Hello, everyone. Welcome to this online course on building materials. I'm your lecturer for today, Huang Xinghao. In this lesson, we will study the key technical properties of structural steel. Steel is an important material widely used in construction engineering. Bridges, frame structures, reinforced concrete structures, and many other engineering projects all rely on steel. The technical properties of steel directly determine the safety and quality of engineering works. In this lesson, we will examine the key technical properties of structural steel from two aspects: mechanical properties and technological properties. Mastering this knowledge will enable us to make scientific and reasonable decisions in material selection and construction practices. In this session, we'll focus on three learning objectives. Knowledge objective: master the core performance indicators of structural steel and understand the significance of its key parameters. Skill objective: be able to identify and analyze the properties of steel and evaluate its suitability for engineering applications. Quality objective: develop an awareness of quality and safety, and cultivate craftsmanship and a strong sense of professional responsibility. Let's begin with the mechanical properties of steel. The mechanical properties of steel are its core properties and directly determine its load-bearing capacity. They mainly include tensile properties, impact toughness, and fatigue strength. Tensile properties are the most important mechanical properties of structural steel. Taking low-carbon steel as an example, we can divide its tensile process into four stages: the elastic stage, the yield stage, the strengthening stage, and the necking stage. During the elastic stage, stress is proportional to strain. The applied load in this stage is relatively small. When the external force is removed, the specimen returns to its original shape. This property is called elasticity, and the deformation in this stage is known as elastic deformation. The modulus of elasticity E reflects the ability of steel to resist elastic deformation. The greater the modulus of elasticity, the better the rigidity of the steel. During the yield stage, once the stress exceeds the elastic limit, stress and strain are no longer proportional. Even without an increase in stress, plastic deformation increases considerably, and the steel undergoes the phenomenon known as yielding. The minimum stress value at this stage is called the yield limit or yield point, denoted by sigma s. When the stress in steel reaches the yield point, although fracture has not yet occurred, the excessive deformation produced renders the structural member unable to meet service requirements. The yield strength sigma s is the reference value for steel strength in structural design. During the strengthening stage, the steel regains its ability to resist plastic deformation. The tensile strength sigma b is the maximum stress that the steel can withstand. The yield ratio reflects the utilization efficiency and safety level of steel. The smaller the ratio, the safer the structure. However, an excessively small ratio may lead to material waste. For structural steel used in construction, a reasonable yield ratio ranges from 0.60 to 0.75. During the necking stage, the cross-sectional area of the specimen decreases sharply until fracture occurs. Elongation delta is a key indicator for evaluating the plasticity of steel. The greater the elongation, the better the plasticity of the steel. Special attention should be paid to the three important indicators obtained from the tensile test of steel. 1. Yield strength. This is the reference value for steel strength in structural design. 2. Tensile strength. This represents the maximum stress that the steel can withstand. 3. Elongation. This is an indicator used to evaluate the plasticity of steel. Hard steels such as medium carbon steel and high carbon steel do not exhibit a distinct yield point, and fracture occurs without a clear yield stage. Therefore, The design code specifies the stress corresponding to 0.2% permanent strain as the nominal yield strength. Impact toughness refers to the ability of steel to resist impact loading. It is expressed by the impact energy alpha K consumed per unit cross-sectional area when the specimen fractures under impact loading. The greater the value of alpha K, the better the impact toughness of the steel. The impact toughness of steel is mainly affected by the following factors. 1. Chemical composition. When the sulfur and phosphorus contents in steel are relatively high, the impact toughness decreases significantly. 2. Microstructure condition. When chemical segregation exists in the steel, the impact toughness is greatly reduced. 3. Rolling and welding quality. Steel generally exhibits higher impact toughness along the rolling direction. The uniformity of the microstructure in welded joints has a significant influence on impact toughness. 4. Temperature. The impact toughness of steel decreases with decreasing temperature. Initially, impact toughness decreases gradually as temperature drops. However, when the temperature falls within a certain range, a narrow temperature interval, the impact toughness decreases sharply and the steel transitions to brittle behavior, a phenomenon known as cold brittleness. The corresponding temperature is called the ductile to brittle transition temperature, DBTT. The lower the DBTT, the better the low temperature impact toughness of the steel. Fatigue strength. Under repeated alternating loads, steel may undergo brittle fracture even when the stress is lower than the yield strength. This type of failure is known as fatigue failure and can be extremely hazardous. The maximum cyclic stress that steel can withstand under an infinite number of alternating load cycles without fracturing is defined as the fatigue strength limit. In engineering practice, the fatigue resistance of steel must be taken into account to prevent fatigue failure in structures. Let's proceed with the technological properties of steel. The technological properties of steel reflect its adaptability during processing and serve as an essential prerequisite for ensuring construction quality. They primarily include cold bending performance and weldability. 1. Cold bending performance refers to the ability of steel to undergo bending deformation at room temperature without fracturing. The test method involves bending a steel bar around a mandrel of specified diameter through an angle of 90 degrees or 180 degrees. If no cracks, fractures, or delamination appear on the outer surface of the bent section, the specimen is considered qualified. The significance of the cold bending test lies not only in evaluating the plastic deformation capacity of steel during bending, but also in revealing internal defects such as microstructural non-uniformity, residual stress, and inclusions. In addition, it can rigorously assess welding quality and detect problems such as incomplete fusion and cracks in welded joints. 2. Weldability refers to the ability of two metal components to form a sound and reliable joint by locally heating them to a molten or semi-molten state. The main welding joint types are lac joints and butt joints. A qualified weld must meet two requirements. First, the weld must be free of cracks and show no tendency toward hard or brittle behavior. Second, the strength of the weld must not be lower than that of the base steel. The weldability of steel is primarily influenced by two factors. The first is chemical composition. Excessively high carbon content increases the risk of weld cracking. Impurities such as sulfur and phosphorus deteriorate weldability, and excessively high alloy element content generally reduces weldability. The second is welding procedure. The reasonable selection of welding methods and welding consumables, together with proper control of welding parameters such as current and voltage, can effectively ensure weld quality. In this lesson, we have learned two core aspects of structural steel. Mechanical properties are the fundamental characteristics of steel and determine structural load-bearing capacity and safety. The key indicators include yield strength, tensile strength, elongation, and impact toughness. Technological properties ensure construction quality. Cold bending performance and weldability directly affect the processing quality of steel materials. Remember, every performance indicator of steel is closely linked to the safety of building structures. Quality is the lifeline of construction. As future engineering professionals, we must establish an unwavering commitment to the principles of quality first, safety first. From material selection and processing to construction, every stage must be guided by a spirit of craftsmanship and continuous improvement, and we should approach every task with a rigorous scientific attitude. Construction engineering is directly related to the safety of people's lives and property. We bear significant social responsibility and must uphold the highest standards of professional duty and accountability to ensure the quality of engineering projects. That's all for today's lesson. Thanks for your attention. See you next time.